problem is a problem in advanced placement chemistry, advanced general chemistry, and may also be used as an Olympiad problem. It is in thermochemistry, and this is the entire problem statement. The normal boiling point of ethanol CH3CH2OH is 78.4 degrees Celsius. The standard entropy of formation of ethanol in the gaseous phase and ethanol in the liquid phase are as follows: 282.7 joules per mole Kelvin and 160.7 joules per mole Kelvin. In advanced thermodynamic textbooks, many times a hat is used above thermodynamic quantities to denote that quantity on a molar basis. Standard in this table was relative to 1 atmospheric pressure, or 101.325 pascals, in the thermodynamic tables from which this data was obtained. On an average day, the atmospheric pressure in Denver, Colorado is 0.8316 atmospheres. Using only the physical data provided in this problem, determine the temperature at which ethanol boils in Denver. The entropies of formation may be assumed constant for the temperature range of interest in this problem. So where does one start? Well, since one is going to be talking about boiling, it's a good place to start with the equilibrium between vapor and liquid. So at the boiling point, a liquid is in equilibrium with its vapor. The normal boiling point is the temperature at which the vapor pressure above the liquid is 1 atmosphere, 1 atmosphere being 101.325 pascals. Currently, this standard pressure is 10 to the 5th Pa, not 10 to the 6th, 10 to the 5th, which is equivalent to 0.9869 atmospheres. For the purposes of this problem, however, normal refers to 1 atmosphere simply because the thermodynamic tables that were used to obtain the entropies of formation used 1 atmosphere as their standard pressure. So the equilibrium is written here, and I'm going to specify that it's at 1 atmosphere for the purposes of this little derivation. At equilibrium, the Gibbs free energy change of a reaction is equal to 0. So additionally, one should recall that the delta G is equal to delta H minus T delta S, where T is equal to constant, a constant, so constant temperature. At equilibrium, therefore, one can simply write that delta H is equal to T delta S. Now note that I've written these equations at a standard pressure, and I've written them on a per mole basis. Okay. With the reaction written from left to right, it may represent, therefore, vaporization. Okay? Vaporization, liquid to gas. As such, okay, one can then write the equation for the delta H of vaporization being the standard enthalpy of formation of the gas minus the standard enthalpy of formation of the liquid. So when one is going from the liquid to the gaseous state, the final state is the gas, the initial state is the liquid. Talking about a change, it's always from final to initial. So in this case, gaseous to liquid state. Likewise, the standard enthalpy of vaporization of ethanol is equal to the standard enthalpy of formation of ethanol gas minus the standard enthalpy of formation of ethanol liquid. And because these quantities were already given in the problem statement, the delta S of vaporization of ethanol standard state is easily computed. 282.7 joules per mole Kelvin minus 160.7 joules per mole Kelvin is equal to 122 joules per mole Kelvin. Now that we have the standard entropy of vaporization, it is quite simple to compute the delta H of vaporization. using the equilibrium condition. Delta H of vaporization is equal to T delta S of vaporization. So therefore, temperature 351.55 Kelvin, which is 78.4 degrees Celsius, times 122 joules per mole Kelvin, 122 was the delta S of vaporization, is the delta S of vaporization at 1 atmosphere. And when that is computed to be 42,889 joules per mole. That is the delta H of vaporization at standard pressure. Now, in Denver, where the pressure is lower, ethanol will boil at a different temperature. In other words, the temperature at which the standard vapor pressure, the ethanol vapor pressure is 0.8316 atmosphere, needs to be determined. Okay. Normally, when there is a lower pressure, the liquid will boil at a lower temperature. Okay. Now, one needs to recall that the natural logarithm of the pressure is proportional to the inverse absolute temperature. This is the observed relation in many cases for certain specific ranges of temperature between vapor pressure and temperature, in this case absolute temperature. The constant of proportionality is negative delta H of vaporization divided by R. So because the constant of proportionality is a constant, in the case where this relation is linear, if it's directly proportional, it's linear. If we take y being equal to ln of p and x being 1 over t, it is simple, therefore, to write a simple linear relation between ln of p and 1 over t. Okay, so ln of p is equal to negative delta H standard of vaporization over RT plus B. This is just the equation of a line. Now, this equation may be applied at two separate points. Let's call the 2 points T1, P1 and T2, P2. And then that equation may be applied at these two different points. Okay, so we have ln of P2 negative delta H of vaporization RT2 plus B. And similarly, at point T1, P1. When these two equations are subtracted, what happens? We obtain the Clausius Clapeyron equation. Okay. Now, from the problem statement, with state 1 being the normal boiling point, we have a P1 of 1 atmosphere, a T1 of 351.55 Kelvin. The P2 is the pressure in Denver, which is 0.8316 atmosphere, and an unknown T2. That is what needs to be solved for. Okay, in other words, the temperature at which the vapor is in equilibrium with the liquid at a pressure of 0.8316 atmosphere for ethanol. So now, knowing that the unknown is T2, one may algebraically solve the Clausius Clapeyron equation for T2. And simple algebraic steps show this result for T2. Notice that ln of P2 minus ln of P1 is ln of P2 divided by P1. So T2 is simply going to be negative R over delta H of vaporization ln P2 over P1 plus 1 over T1, this entire quantity raised to the negative 1 power. All one has to do now is substitute in the values from this problem statement. It is very convenient to keep the units in this problem because this is a way to check if one is actually working the problem in the correct manner and not making a mistake with numbers, with units. So negative 8.314 joule per mole K divided by the delta H of vaporization, 42,889 joule per mole. This joule per mole cancels out. We have inverse Kelvin here, ln of P2 over P1. Okay, this cancels out the atmospheres. And then plus 1 over T1. Okay, so inverse Kelvin. The inverse of inverse Kelvin gives you Kelvin. So when all of this is put in the calculator, the final answer is 74.04 degrees Celsius. So this is the temperature at which ethanol vapor will boil in Denver for the average pressure shown in this problem statement.